Yeah, exactly. So I'm Christoph Bergmeir. We are going to talk today about machine learning for forecasting. Um, One thing I should say is I got about 2 hours of material, I think. So yeah, bear with me. The other thing is we had planned maybe some lab or something, but then we thought, well, we have so much material, let's just stick to this. So we won't have any like lab type of things. So that means my PhD student Abishek, he will just present some of the theory as well. Initially, we had planned for lab. Good. With that, let's get into it with some introduction. So the talk today is mainly about what some people would call plain old machine learning, POML. So we will cover deep learning a little bit, but not in much detail. I mean, I think there are better resources out there probably and people more competent to talk about it. We will also not talk a lot about like generative foundational models, GPT-like things. I will talk about that in a moment quite quickly, but then we will talk about other things. So if that's what you came here for, then sorry to make you unhappy, and but I hope you find it still enjoyable. So I think the main intention of this training course is that you understand like the basic problems and general solutions in forecasting for both modeling and evaluation, so that you are able to judge results of complicated ML methods, right? So my idea of today's talk is something like if this shiny new deep learning method comes along in a new paper, that you are enabled to say, hold on, what do they actually do? Does this make sense for me to try to use that? Yeah. So why should we exactly? So why should we still look at plain old? Well, and when I say plain old machine learning, I'm talking about any machine learning that is not deep learning, things like gradient boosted trees and maybe even feed forward neural networks, things like that. Yeah, so why should we still look into this if nowadays it's all about deep learning? And sure, I mean, transformers, graph neural networks, they may be all the fuss and a lot of papers coming out in this space. However, one thing that I have found is that many of these recent transformer papers have flawed experimental setups and greatly misrepresenting their capabilities on the used data sets, which means their evaluation is often quite weak, and what they promise, they often cannot really hold. For example, they use only series with thousands of data points per series. And while, you know, companies like Amazon, Google, also Zalando, they may be getting good results with these transformers, but they have like hundreds of thousands of series. Another thing to keep in mind is that these models, they have been largely irrelevant in the M5 competition, even though many of these architectures were already available at that time. I mean, obviously, there have been coming out a lot more since then, but some things, yeah, were definitely already there. So the question is, why did people not use them? So if you think about your typical forecasting problem, that could be something like this. I have about 1,000 series, there are daily series. Should I try the deep learning model or not? To me, I think that the answer is not so clear right now. So maybe it works, maybe it doesn't. And you can also have a look at our data repository at forecastingdata.org, where we also ran some of these methods, and the results are quite mixed, right? So sometimes these methods work quite well, sometimes other things work better. Yeah, and the other thing to address is obviously like why should we even bother about this if in 2 years everything will be done with some GPT variant anyway? So won't all of this be soon obsolete? I guess, look, the answer is these foundational time series models, they are definitely coming. I mean, we've seen time GPT coming out. But you see, now I have all these questions, like, will they work on any possible frequency? Because one thing that you have to understand about forecasting is that forecasting can mean a lot of things to a lot of people. So you could have like one yearly time series with 15 data points in total. You could have one time series with 1 million data points and 10 covariates. You could have 100,000 time series that are all, 50 data points long. And they could have all of these different frequencies. You could have yearly series, monthly, daily, half-hourly, minutely, secondly. So will they work with all of these possible frequencies? I think, well, maybe they could. I think, well, at least on maybe the 20 most common ones. Another really big question for me is, will they work with covariates? Because in many forecasting problems, you have, things like the weather is available, or promotions that you know of, different things. How will they deal with this? I think it's not so clear right now. So maybe with some form of embedding or dimensionality reduction. I've just 2 days ago, I learned about TAP-PFN, which is like a transformer for tabular data that works up to 100 features. So I think that's a very interesting thing. Maybe that can in some way be adapted to GPT. You could try some stacking where basically you just take whatever this GPT method gives you and you feed that into your own algorithm as an additional input. So I think there are definitely, ways to address this, but right now we don't know any of these things. And then obviously the other big question is, will this work with your constraints that you have in production, with your hardware, your timeframes, your privacy, data sharing concerns? So I think many companies will not be happy to just send all of their time series to some external service to get them forecasted. Will you need, do you need a 5-minute lead prediction real time? Does it need to run on some edge device on your wind farm? All of these things, depends on whether it makes sense to run these models. And then, well, one thing would be obviously then, will there be open source pre-trained models out there at some point to get around some of these things? So right now, still we don't know, and I'm sure there will be very interesting things happening the years to come. But well, I mean, right now we have solutions that work with machine learning. So I will just talk about where we're at right now, and many of these things I'm sure can be also useful to what's to come. Good. So let me very briefly talk about my background. Why should you be? Yeah, okay, exactly. Very good question from Baman. Like, how interpretable will these models be? Like time GPT results. Exactly. I think that's a very big research question as well right now, and not only in the time series domain, right? For these large language models, people also ask these questions. I was in a talk, 2 days ago, where they asked some of these questions. I think there will be some answers at some point, but it's still just, quite open fields of research. Okay, now quickly about my background. So, why should you bother listening to my talk? So I have been in forecasting since the start of my PhD here at University of Granada about 2009. I then went on to Monash University working, for example, with Rob Hindman. I recently did a sabbatical in industry working at Meta. Now I'm back at University of Granada doing research in forecasting. And so some topics I have worked on would be forecasting for fault detection in wind turbines, for pest outbreaks in greenhouses, for predictive maintenance and renewable energy production forecasting for wind and solar, energy demand forecasting, energy price forecasting, also retail demand forecasting, supply chain type of applications. So that gives you kind of an idea of what I forecast, right? So I think forecasting, we can do sales forecasting and supply chain and retail. In energy, there are many forecasting problems like demand, price, renewable energy production, also building efficiency, predictive maintenance for road, railroad, mining, other types of machinery. But strangely enough, there are also some, or well, interesting enough, there are also quite some things that I don't forecast. And that's what usually people ask me first, like, oh, do you do this? Do you do that? And two notable examples are the weather. So because for the weather, we have lots of domain knowledge and specialized models. So we leave it to the experts in that domain, which are the meteorologists. But we often use weather forecasts as some external inputs to our models. Another thing I don't really forecast is the stock market. And why is that? So, I mean, there are some obvious pros to forecasting the stock market. You have heaps of freely available high frequency data. You have a very clear motivation and a use case, which is you want to make money. So I think that's why a lot of academics, machine learning academics wanting to write papers about forecasting, that's why they are drawn to stock market forecasting, because they just have the data anywhere available and it's an obvious use case. So, but there are also a lot of drawbacks to stock market forecasting. So the share price is usually not a function of its own past, but of its anticipated future. Right. So, you have very extremely low signal to noise ratio. And another thing that machine learners that are not like in finance, for example, do often not understand is that there is markets tend to be close to efficient. And what that means, so efficient market means that any information that is available is already included in the current price. So that means in an efficient market, you should not be able to do forecasting beyond a knife forecast. And then, people got, like Robert Engle got a Nobel Prize in 2003 for methods of analyzing economic time series with time varying volatility, which is about volatility forecasting, right? So in finance, it's usually all about predicting volatility, predicting risk, and not returns. Because there is kind of this consensus that predicting stock market returns from just using some lags, which means just the past of the series, that will not work no matter what method you're using. Obviously, what could work is if you get some very good covariates. I mean, what people do is they kind of check sentiment on social media, like on Twitter, and then they try to use this sentiment to predict stock prices. I mean, I think it's all about like getting the right covariates. But if you just use the past of a stock price, that's not going to work very well. All this is also true in similar ways for exchange rates, right? I mean, exchange rates are in this sense quite similar to stock prices. This is very important still. We will get back to this later. So a lot of like very recent literature and very good machine learning conferences try to predict exchange rates. It doesn't work. we get to it soon enough, in about an hour. So as I said, that this talk is the main audience of this talk is machine learners who are kind of new to forecasting in a certain way. Let me start off with a bit of forecasting terminology, right? So if forecasters talk about model fitting, parameter estimation, that would be what a machine learner calls model training. In sample would be the training set, out of sample would be the test set. Forecast horizon, that's kind of the target variable, like do you want to forecast 1 day ahead, 2 days ahead? Forecast origin, that's from where you do your forecasting from. So that's usually the last known observation, like the value from today, for example. Rolling origin would be that your forecast origin changes. So for example, over the test set, you forecast from every point in the test set with the information known up to that point. And then fixed origin is just the forecast origin is fixed, so it doesn't change. And that's terminology I will use throughout this talk. Some more terminology. forecast combination, that's what machine learners call ensembling, lags, independent variables, regressors, covariates, predictors. That's what machine learners would call features or inputs. A dummy variable, an indicator variable, that's what machine learners would call one-hot encoding. Seasonality, seasonal period, that's a cyclic change in the mean of the series, and its length is known a priori and will not change in the future. So I think this is very important. So people in machine learning, people often think like, oh, we have to find the seasonality and then it could change. And then I'm always like, no, that doesn't make a lot of sense. I mean, if I have a daily series, I have a lot of reason to assume that I have a seasonal cycle of length 7, right? And let's say I have a series that has only trading days, well, or only weekdays, my seasonal cycle would be 5. And if I go now 5 years into the future, this cycle would still be 5 or would still be 7, right? So it's a quite strong assumption that makes sense. But now if you say, oh, this seasonal cycle, I just detect it from the data and then I have it variable and it can change. It can sometimes be 7, sometimes 8. It's usually not at all justified. Yeah. So that's the idea of seasonality. It doesn't change and it's known beforehand. Trend is usually a smooth change in the mean of the series. Yeah. Good. So now I want to spend a little bit of time, not too much, to just talk about the the most basic forecasting methods that have come out of the field of forecasting, right? So there is something called the naive forecast, where we just use the last known observation as our forecast. And if you think about it, what you effectively do, you're weighting your last observation with a 1 and all the other observations with a 0, right? So because you only take the last observation and you ignore the other observations that you have. So a mean forecast is kind of the opposite. So you just calculate the mean over all your time series and you say, this is my forecast. And that means you weigh all the observations equally. But now if you think about it, mean and naive forecast, obviously 2 extreme cases, right? In one, only the last observation, in the other one, all the observations equally. So because the central assumption in forecasting is often that the more recent past is more important than the more distant past. So a quite obvious idea is, what about we just weight the observations, for example, with an exponential decay? And this is what we would call exponential smoothing. So here is an example. So this is a time series. This is our forecast, this flat blue line. And the red line, what this shows you is kind of the exponential weights. I mean, I've shifted them down so that you can see them better in the plot. So they are not really at -4, and you see kind of the last observation gets the most weight, and then you weight it down. And that's why the forecast is not exactly the last observation, but it's shifted a bit down. Yeah. Okay, and this is what is called simple exponential smoothing. Now exponential smoothing is basically this idea of simple exponential smoothing applied to components. So you would have a level, seasonality, and trend component. It dates back to 1957, this method, and it was used for a long time as a quite ad hoc method without any theoretical underpinning. That was then one of, maybe the most important work of Rob Hindman to give it this solid statistical foundation in state space models. And ETS actually stands for exponential smoothing, or for error, trend, and seasonality, which are usually, the different parts that you fit. Yeah. So another very important method is autoregressive moving average, or AMA method. So here the idea is that you basically just, you have a linear model where you basically, you get your current observation, x at time t, you go back to x t minus p plus 1. So this is like your input window. You just have like a a linear model over this input window that you shift through the series. And then you also have a linear model over the errors that you made over the last observations. And now people always say, well, this is a linear model. So in many papers, you would read things like, oh, these traditional methods are all linear, and now we do machine learning. This is not linear. Well, and for me, it's always, when I read this sentence, I'm always like, well, but hold on. I mean, ETS, that even has exponential in its name. And it's not really linear. But if we now talk about linear, what does linear even mean, right? So for example, this model that we're looking at here, this is linear in the lags and it's linear in the errors. But when you now actually start fitting an ARMA model, then you are like, well, hold on, where do I get these errors from? So these errors, you need to actually step through the series to get these errors. So you need to estimate some initial conditions and step through the whole series. There's no closed form solution. If you look at the R code of ARMA, it actually uses a BFGS nonlinear fitting procedure. So, and that's what makes ARMA models often actually quite slow. So if you have a very long time series, fitting an ARMA model is quite slow. So yeah, so for me, it's always when people say, well, it's a linear model. Well, but you fit it as a nonlinear model. And it's certainly not linear, you know, just in time, in the time steps. So yeah, I never liked this sentence. Okay, anyway, so now we've seen what, so basically this part here is the AR part. This is called the AR part, the linear model over the lags. The linear model over the errors, that's called the MA part. So now there's a RIMA model. So now what does the I stand for? The I is integrated. So the question is, do you want to model the values directly or do you want to model the change over the last values? So basically you're just differencing the series before you use the RIMA. So this addresses non-stationarity, but it's actually just like a pre-processing step, right? So you difference the series before you do the ARMA. Why would you difference? Because hopefully it makes the series stationary. The problem is you do lose some information about the scale in the series in your pre-processing. And you know, sometimes you would see papers where people say, oh, like machine learning methods, neural network, they can only deal with stationary data. So let's run an ARIMA because that works on non-stationary data. And then whatever comes out of the ARIMA, we fit that into the neural network. And then I think, well, but the only thing that the ARIMA does to make a series stationary is it does differencing of the series. So why don't you just difference the series? And then you run your neural network on this difference series, right? Okay, good. We get back to that a bit later. So now one other thing that I think is important mentioning is this result that any stationary AR1 model has an equivalent MA infinity model and any invertible MA1 model has an equivalent AR infinity model. So that means you can actually approximate this MA part in the ARMA model with a higher order AR part. In practice, this higher order is often not even that high. So, well, you can use, I don't know, 20 or 50 or something like that. Like in econometrics, people often use AR2, AR3, and then AR5 is already quite high order. So in that sense, you don't really need this MA part. I see it often more like a reparameterization to get fewer parameters, smaller input windows at the cost of more complex model fitting. Okay, I think that's everything I wanted to say about like these traditional methods, just that we are kind of all on the same page when I say ARIMA ETS. For more details, standard resources, obviously Rob Hindman's and George Athanasopoulos' book, that is very good, that I can recommend you. I put here FBP2, that still uses the old forecast package. There's FBP3 that uses the Fable package. Anyway, yeah. Good. So now I wanted to go through a quite brief history of machine learning and forecasting before then we get to really the methods and and how it's all done. So, I mean, well, history of machine learning and forecasting. In forecasting, we obviously had these M competitions. So it started with the M1 in '82. M stands for Makridakis, who runs these competitions. So, and in the M3 and one thing I should say is, I think it is important to understand a little bit the history of machine learning and forecasting, because if you are a forecaster, you will often see that if you are a machine learner, you will often see that forecasters are a bit, reserved to new machine learning results, claiming that they have, solved forecasting, because this has a long tradition. So I think understanding the history a bit gives you a bit of context of why, as a machine learner, you might get some backlash. Okay, so I want to start talking about the M3 competition. There were M1, M2 competitions before. And this M3 competition had as a central conclusion that complex methods do not necessarily outperform simple methods. And in that context, actually, ETS and ARIMA were considered complex models. And the simple models were things like a random walk with drift, which means, so random walk means like a naive forecast. You just take the last observation, and drift means you put a kind of a constant change on it. So there was only one neural network participating in this competition. It was quite bad. The competition was won by the theta method, which was later shown to be an average of a linear regression and simple exponential smoothing with drift. And now this M3 data set that consists of yearly, quarterly, monthly data. The yearly data have as low as 15 data points. The monthly data has maybe 120 data points per series. Now, this data set was basically the benchmark data set in forecasting for almost 20 years. It has seen a lot of focus, maybe a bit too much. And I think on this data set, to perform well as machine learning methods is quite difficult. So, yeah. So basically, since the M3, people thought forecasting methods need to be simple. Neural networks don't work very well. And this idea continued up until easily 2010, 2012 maybe. So there was this long-standing controversy in the forecasting field whether machine learning or statistical methods work better. And I think, yeah, the idea is that the forecasters knew that simple methods work best, well, because of the N3, but also afterwards there were competitions called NN3, NN5, particularly for machine learning methods, and even those were won by simpler methods. And machine learners, well, knew that neural networks work best, because machine learners always know that neural networks work best because it's a universal approximator. So there are all these papers out there in the literature, in the neural network literature, that are things like, a novel method X for stock market forecasting. Yeah, they often use cherry-pick data sets, no proper benchmarking. If you see a paper that talks about stock market forecasting, and then they say, oh, and we've tested our method on these 3 stock market time series, then for me, the first question is always, well, if I go onto Yahoo Finance, I can easily download 500, 1,000 stock market time series. Why are you using these 3, right? And if the paper doesn't present you with a really good answer, chances are that it's just the 3 methods series where their method worked well. Yeah, just as a side note, also every time I hear somebody say Informer is the state of the art in forecasting, I get reminded that this is still very relevant today because, well, I don't want to open a can of worms here, but the original Informer paper does not have a good benchmarks and good experimentation. So I don't think it's sufficient to really show that the method works. It's also not showing that the method doesn't work, right? I'm not saying this, but yeah. Okay, so yeah, there was this controversy, and that actually motivated Spiros Makridakis to write a paper in 2018 about statistical and machine learning forecasting methods, where he benchmarked ML methods again against statistical benchmarks. In this paper, the machine learning methods lost. And the paper is published in PLOS One because it actually got rejected at 2 to 3 neural network outlets beforehand. Reasons for rejection were that, there are many ML methods that have proven to overcome the results provided. That's what the editors and the reviewers said. They didn't name any in particular. So it seems Makridakis was quite upset over this, and he did what he seemingly does best when he is upset. He organized another competition, the M4 this time. So the context here is that in the M1 already it was similar. So basically he had written a paper about ARIMA not working very well. He got a lot of backlash, and then he organized the M competition. Okay, so the idea of the M4 was obviously machine learners can submit their forecasts that show their methods work well, and we settled this kind of question, right? Yeah. Exactly. So I think this is a bit of context that should show you why the forecasting field kind of got quite hung up on this controversy. I still find it a bit surprising, as forecasting actually emerged from statistics just the same way that machine learning later emerged from statistics, namely by a focus on out-of-sample accuracy instead of model properties. And that actually also led to some things being discovered quite independently in both fields. I think the best example is forecast combination. In forecasting, that has been around since 1969, whereas sampling in machine learning was invented kind of in the 90s. Forecasting for a long time had this idea we need simple methods, whereas in machine learning you had this idea of, well, you need to regularize. Yeah, so forecasters have really been used to ML promising much and hardly delivering anything. However, this has really changed in recent years since M4. I would argue, well, that also the arrogance and ignorance that machine learners often have, kind of this disruptive mindset, like, oh, I just go into this research field with my transformer and I eclipse all the 40 years of research that have happened there before. This hasn't helped either. It's still not helping. And also keep in mind, forecasting, it's usually not like image classification or NLP, where you do have just very complex input data structures, but zero noise and no covariates and so on. So forecasting is a bit difficult. Still, machine learning now is usually the way to go. I still think forecasting and machine learning can still learn a lot from each other. So also as a machine learner, it makes a lot of sense to look at what's there in forecasting. Okay, so let's get back to the M4 competition. That was about 100,000 series across many different domains. Yeah, I have a question. Okay. Good. Yeah, so M4 competition. So 100,000 series across many different domains. Hourly, daily, weekly, monthly, quarterly, yearly series. You also needed to provide prediction intervals. The results, I would argue that most forecasters back then expected that a combination approach of statistical methods would win. However, those actually got second and third, and to everybody's big surprise, the winner was well, now it's called ESRNN, that is a hybrid between a recurrent neural network and exponential smoothing by Slavik Smil. Yeah, it was a big surprise to many people that machine learning is competitive and that it works so well. I kind of saw it coming for the simple reason that 2 years before there was a much less kind of noticed competition, the CIF 2016 competition, where actually I got beaten already by Slavik Smil. it's an interesting competition because it was just 72 monthly series of lengths about 22 to 108 data points. So when I saw this competition, I was like, no way that machine learning works well on this data set, like 72 series with these short series. So I participated just with plain ETS and with backed ETS, which was an algorithm I had developed earlier together with some other people. And so actually backed ETS won several subcategories, and it also won on median estimate. However, the competition metric was mean estimate, and backed ETS actually was quite bad. It got 9s, and ETS got 3rd. And first and second place were LSTMs from Slavic Smul, globally trained across all the series. So, and you see, I think this is still a very interesting use case, because here, this is a small data set, and still machine learning is able to outperform everything else. And this was quite new. So yeah, I think the most important thing here is globally trained across series, right? So yeah, and this gets us to the next part, which is now global models, right? So I think this is a very important concept now in forecasting as well. The term global models was introduced by Tim Januszowski in 2020. It is arguably not a very good name for various reasons, but it's still the name we got, so we stick to it for now. So the idea was that traditionally you take one time series and you see that as a data set. What that means is you build one model for each time series, and then in the M4, for example, you have these 100,000 series. You try to make them very diverse so that you can, get a good picture of which method works well on which. But the idea was you train one model per series. And now what happens is that actually the low sampling frequency and the non-stationarities and structural breaks make usually that we just don't have enough data to fit complex machine learning models. Yeah, and as I said, M3 and 4 data sets are put together under this paradigm. Very different series, very different frequencies. So yeah, and think about it. If you have like a monthly series, or let's say you have a yearly series, like how many years of data can you realistically get? 5 years? 20 years? 20 years on a yearly series means 20 data points. And even if you can get 20 years of data, like how relevant will the data from 15 years ago still be to your current forecasting, right? Probably the whole business has changed. Like a lot of things have changed, so that the past from 10 years ago is just not relevant. So this is kind of the limiting factor normally in getting data in forecasting. Yeah, but now the idea in global models is that you really have this paradigm shift of you see a set of time series as a data set. For example, a set of series in retail, smart meters, and so on. And now you build one model across all of these series. As I said, we call that global modeling, also cross-learning, multitask learning. With linear models, we often call it pooled regression. Yeah, and now suddenly you have enough data, and the machine learning models are actually quite competitive. So, and I think the way to think about it is the following. If you have a local model that trains per series, let's say you fit ETS. ETS will maybe have only 5 parameters, or maybe, less than 10 parameters. But now if you have 10,000 series, on each series you fit a model with 5 parameters, you end up with 50,000 parameters. So now if you fit a global model, just one model across your about your 10,000 series, you can obviously use a model, for example, with 5,000 parameters, which is a lot smaller than a model with 50,000 parameters. But now you have one model with 5,000 parameters. So it's a quite large and complex model. Yeah. So, and now the idea is obviously that the complexity in local models grows when the data set grows, because for every new time series you fit a new model, you get, let's say, 5 new parameters. So it grows, whereas if the complexity of a global model can stay the same, right? No, you can just add more series and train the same model. Yeah, so global models can afford to be more complex. And now the question is how to add this complexity well. You can add it as longer memory, so you just make larger input windows. You can obviously use nonlinear or non-parametric models. So you would now use your neural network, gradient boosted tree, or transformer, whatever you want. And you can also do some data partitioning. And what that means is now you're training the global model not anymore globally across all the data, but only on some subsets. And that's the reason why global model is not a good name, because often the global models are not trained globally, but on subsets of your data. One very important point I want to make is that a global model is not a multivariate model. Why is that? Well, so in a global model, you learn across the series, across all series together, but you predict every series in isolation. And that means they can work on data sets where different series have different lengths. They are not aligned like M3 and 4. They do not take into account interactions between the series. And in fact, the concepts are actually orthogonal. So methods can be local univariate, that would be ETS, ARIMA, and so on. Global univariate, that's what we talk mostly about in the following. Local multivariate and global multivariate. Yeah, exactly. Before we talked about local univariate, now global univariate. Later also a bit local multivariate. We won't cover global multivariate. But yeah, let's see if I can actually do this. I wanted to like paint here a little bit. Okay, so I think that's what always helps me quite to understand. So let's say these are all your time series. Okay. Now, if you have a multivariate model, what you would probably do is you do something like this. You need to take an input window that captures all the series together in one input window, because you want to look at kind of the interactions and so on. And now this window, you shift that just that way through your series. So you see in the multivariate model, all of them need to be aligned so that you can take the window at a certain point in time. And now this is how you shift the window. And now you already see one problem of multivariate modeling is often that this input window is incredibly big. Let's say you have 20,000 series, this window is really big. So you need to come up with a way of making this sparse, taking only some of the series and so on. In a global model, this is actually a bit different. So if we again have all our series, in a global model, the input window, well, I should say input window during training is still just on this time series, and then sequentially you go to the next time series, and you basically go through your data like this. Yeah. And then if you if you do forecasting, your input window is just from one series. So you just go through that series that you forecast right now. Right. So that's the difference between global and multivariate models. Okay. So yeah, now, well, some history of global models, they go back to the early 2000s. Then one interesting thing is that actually pooled regression is a quite standard technique in statistics. There's a book from 2007 talking quite a lot about it. It's just people didn't have the idea of using that for forecasting until about 2015. And then obviously 2016 was when, well, Slavek Smil developed some of his ideas in the CIF competition. Then 2017 was DeepAR. When et al. Is MQRNN, that was also 2017. We had some early works as well. And since then, the field has quite exploded and has so much work. Another quite interesting resources are the Kaggle competitions, because, and there's a quite nice paper from 2020 talking about these competitions, because there were competitions already in 2014, 2015, 2017, where people actually used global models, gradient boosted trees, neural networks, that work quite well. And then obviously in the M5 that was held in 2020, that was dominated by light GBMs. Deep AR, NB, also was successful. As I said before, it's interesting that the temporal fusion transformer, TFT, that was already around at that time. Nobody used it. With one of my students, I tried to use it. We couldn't get good results. So yeah, a team of my students, they actually won 17th place out of over 5,000 participants. And what they did was they used an ensemble of a light GBM and a pooled linear regression. And the interesting thing is that actually just this linear regression would have been 19th place. Yeah. Okay, does the term transfer learning apply when using global models? That's a very good question. I think it does, right? So I remember writing a paper recently about, so you see that there are a lot of, I mean, there's another term called concept drift. And actually, we wrote a paper recently about concept drift in forecasting, because, so there we go. So yeah, concept drift, transfer learning. I mean, in time series, obviously the series would have non-stationarities, so that is kind of the same as concept drift. And the difference is more that these machine learning methods, they usually don't deal with it. I mean, something like ETS, that automatically follows the series, so you don't need to do like concept drift adaptation of ETS. And yeah, transfer learning is similar. I mean, transfer learning can be used for concept drift. I think global models, obviously, it's similar. I mean, I guess it always depends. For me, a question is often, like people do things like they train on a bunch of time series and then they would test on other time series. And for me, the question would be, why? Why would you do that? Right? So usually you would have history of all of the series that you forecast. So yeah. Well, obviously there could be series where you don't have history and then you, but that's a whole different problem. But yeah, it's definitely related, yeah. Okay. Yeah, so global models have shown success to a quite surprising, unreasonable degree. The idea was for a very long time that these series have to be related or similar in some way so that you can learn something useful across them. Then people started asking, like, what does related mean? Is that correlated, or what does it mean? So it's certainly, yeah, in terms of the of the data generating process. Yeah, and then actually Pablo Montero Manso and Rob Heinemann, they had this paper in 2020 about global models, where they basically showed that global models can produce the same forecast as a local model without any assumption about similarities. So the series don't have to be related. It's much more about fitting complex patterns across series. And the global model will even fit if you have many simple patterns that are quite different across the series. This result, well, is remarkable because similar results in multitask learning for regression don't exist. So it's something that works on forecasting. And I think one very important thing that you have to understand about global modeling is that the question is, what is your evaluation about? If your evaluation is you want to perform well on an average error across all your series, then global modeling will enable you to get this average error across all the series down, right? So that's the point. Like people before always thought, well, I need to be good on every series. And that's what I do with the local models. And now in the end, I average to see what I get. No, if what you in the end are optimizing for is the average error across all your series, that's what a global model can do for you. If you're interested in only the error of 5 series out of your 10,000 series, the global model might not do what you hope it does, right? So, yeah. So it's, I mean, people often say that a global model, it sees these related patterns and it can translate them into other series. I guess that's happening, but it's also really about the global model optimizes directly this average error over everything. Good, okay. So now finally, yeah, let's get into really like the main topic, the machine learning methods for forecasting. Yeah, okay, that is a very good question. Like, how many series do we need for? Okay, so, well, to reiterate, I think about it in terms of how many data points do I have across series, right? Like it can make perfect sense to build a global model just for 2 time series, right? It's much more important how many data points do you have across the series. And then, well, it does depend on how similar are they. Like if these 2 series are very similar, you have to effectively only learn one concept, it's obviously going to be easier if the 2 are very different. Yeah. Okay. Actually, we also have a paper. I didn't cite that here. That's Heva Malage, a simulation study for global models or something like that it's called, where we look at exactly this, like how much data do you really need? How do the series need to be for the global modeling to work? Okay, machine learning methods for forecasting. Yeah, exactly. It is very similar to multitask learning, yes. Good. Machine learning methods for forecasting. So yeah, we've seen nowadays they work. So I think in the forecasting field, there's no question anymore if they do work. They do work. If you do global modeling, you can also use them for single time series if they are long enough, right? If you have one time series that has 500,000 data points, absolutely use machine learning models. And yeah, you often have longer series because of the finer granularities. You can have additional metadata. And then I think the basic setup would be always your nonlinear auto-regression, nonlinear non-parametric auto-regression. So so you just get like lags, have an input window, then you can use your favorite machine learning method out of the box. We've seen that can approximate an ARMA model. You just need to choose more lags. And then it should work quite well. So, yeah. Okay, thanks, Abishek, for sending that link. So, but now, so what is the biggest problem when we use machine learning methods for forecasting? The biggest problem is non-stationarity. So non-stationarity means the data distribution changes over time. And actually, it's funny, but if you think about it, actually, many or even most real-world problems have a time component and changing distributions. So just think about, you develop an algorithm for detecting cars on the street, and you are given a data set from the 1970s. Right? So cars looked very different in the 1970s. Maybe even like people look different. The streets look different. So there is like this kind of concept drift over time, pretty much in everything. But in time series, it's usually much more explicit and has more impact. And to just make this very obvious, so this is a time series. I just generated some random walk series, which means, it could resemble like a stock price. And now this is my training set up to about 800. And now I train my models. I've trained a random forest SVM neural network just with a couple of legs, and now I just test it on the testing set, right? And what do you see here? Well, I mean, like the testing set that has values of close to 80. The algorithm has never seen those values in the training set, so it's not predicting them, right? It's kind of just going flat here. So, I mean, that's maybe a bit a trivial case, but you see, I think that really okay, we got a question about retail. Let's get back to that later, right? I hope we have time, but yeah, it's a very good question, and let's see if we can answer it at the end. So, yeah, so what you see here is that, I mean, it's kind of an obvious example, but I think it shows very well the problem. Like if you try to predict values you have never seen, it's not going to work out of the box, right? And now the problem with non-stationarity is that, I mean, there's this joke. Well, you know, it's a math joke, so I'm not sure how funny it really is. But so there's this joke of dividing the world into linear and non-linear is a bit like dividing the world into bananas and non-bananas. So because, you know, there are so many different forms of non-linearity. So linear, very clear-cut concept. Non-linear, just everything else. And for stationarity, it's like the same thing, right? So it's quite obvious what stationarity is, but then so stationarity is that, you know, the distribution doesn't change over time. But now non-stationarities, there can be so many different ways of non-stationarity. You can have a change in the mean, which is seasonality or trend. You could have a change in variance like heteroscedasticity. You could have stochastic trends. And just if we look at some series, you know, when people say, oh, I do time series forecasting, I have a method for time series forecasting. I mean, looking here at these series, they are so different, right? The first one that has this multiplicative trend and it multiplicative seasonality and like an upwards trend. This second one that is like a stochastic trend, the electricity demand series down here, that has a very prominent daily and weekly seasonality, not so much of a trend. So stationarities can be very different and the way to deal with them changes, right? So one thing that I found, well, and again, sorry for people that I didn't clearly announce that we'll do 2 hours, but yeah, anyway, you can obviously watch the recording. So yeah, so how to achieve stationarity? I mean, or how to deal with non-stationarity, right? So in economics and econometrics and finance, many series kind of look like random walks. So that's why differencing is the common tool there to achieve stationarity. I mean, we've seen the Riemann model earlier that does differencing. And differencing is often kind of seen as, well, this is a way to deal with stationarity, with non-stationarity. But, you know, I mean, it only solves certain forms of non-stationarity and not others. So you are losing information about the scale. I mean, you can solve that by maybe having like another input with the scale. And while differencing can help to make machine learning models more robust, but there are situations where it won't work, right? So this is an example. I mean, if my original, I mean, obviously it's a bit artificial example, but let's say my series is this exponential trend. Now, by definition, if you difference an exponential trend, you get back an exponential trend. So you see like the black is my original series. I do a difference, I get the blue series. I do another difference, I get the red series. And you see differencing doesn't help you. The series is still non-stationary. Yeah. Another example I want to show is this wind power forecasting example here that well, it's kind of artificially made up data. But you see one thing that in wind power, well, you have your wind turbine, you have a very clear minimum and maximum, like you cannot generate less power than 0 power. And the maximum is that wind turbine will generate maybe, you know, 1 megawatt. And that's where it cuts out, right? And that's what we see up here. Like once you hit the maximum, the wind turbine just doesn't produce anymore. Now, if you get a difference of your series, I mean, you see here, this just gives you a 0 here. So you don't really, you lose this information that here in this patch of zeros, the series has no way of going up anymore because it's already at the maximum. It can only go down, right? So with the differencing, you kind of lose this information. Okay. Yeah, now how can you model a trend? Well, the problem is it's not very well specified what a trend even is. So it's usually just like a smoothed version of the series. And the problem is, well, if you detrend, you still need to forecast the trend. And that is often just as difficult as predicting the series itself. So detrending the series, well, it can be done, but it's often not solving the problem. Another option is obviously to do things like logarithms or Box-Cox transforms. It makes exponential trends linear. It stabilizes the variance. Choosing this lambda is often not so easy. But yeah, that's the way how you can model trends. One thing that we do a lot is this window-wise normalization that actually Slavek Smil did back then in 2016 in this CIF competition, and that we've adopted since then. So the idea is you take your input window, and we've talked about it before, having a large input window is often good. So you take a large input window. Now you can just kind of take the mean of that large input window and you normalize by that. And that actually works quite well. So yeah, you want to avoid saturation issues of sigmoid tanh activations. It's quite similar to batch normalization. And now if you think about it, instead of saturating on the absolute value of the training data, as what we've seen before, it's now saturating on the absolute value of the steepness of the trend of the training data, which is often not such a bad idea. Like you should probably not predict trends that are steeper than anything you've seen before. That's like a recipe of getting a very bad forecast. Yeah, and if you combine that with something like a log that you do before, yeah, you can predict very steep trends. So what you see here is the black, that's all the training data. And now you see, well, you can't really see it, but the green line, it really follows very closely that blue line. So the machine learning method is now really predicting this super steep trend, even if it hasn't seen ever anything like that. Yeah, so like window-wise normalization, that works really well. You see what, this is like an example, right? So we've seen the air passenger series before. That was like, well, maybe if we go back quickly, that was here, this top series. So it has a quite steep trend. And now if you do window-wise normalization, the series actually looks like this. So, and like that, it's obviously a lot better to model. Yeah. Yeah, what else is there to be said about trends? So be careful with strong trends because exponential trends in your series will slow eventually. Like every exponential trend will slow eventually, just because you will run out of. So for example, if you want to forecast Facebook growth, has Facebook had like a exponential growth over the last 20 years? Yes. Well, let's assume yes. But now at some point they will just run out of people in the world to give accounts to. So that trend will slow eventually, right? So that's like a knowledge we have that trends will slow eventually. Even linear trends are usually quite bold assumptions. So experts have come up with this idea of damped trends. So what's important about damped trends is that they are usually not justified from the data. You just build them into your model to be conservative about the forecasting. And the idea is forecasting should always be conservative. Okay, we got a very good question about so basically that in statistics you can often like make assumptions about the outcome. Yeah, well, I guess in global models the idea is to model everything from the data. I mean, talking about assumptions, I've talked about seasonalities, I've talked about trends that could slow. I mean, that would be assumptions you might want to build into the model. Another thing is obviously the probabilistic forecasting, to which we will hopefully get soon as well. Okay, now how do you model seasonality? So there was some discussions about whether neural networks can model seasonality at all or not. Some early work suggested they can model seasonality. Later work suggested you need to deseasonalize your data first. We now came to the conclusion machine learning models can obviously model seasonality, but if they have enough data. Yeah, so we did this simple experiment. We generated a sine wave, let the neural network learn it. So, you know, maybe 2 full periods is not enough, but 20 full periods can be enough. Yeah, so we usually assume we know the seasonality beforehand. Yeah, and then the question is, you know, should you deseasonalize the data before you run the model or not? So it depends on how much data you have, right? So you can, and then, yeah, how to model seasonality. You can have these seasonal indicators where you just have a categorical variable telling you whether this is Monday, Tuesday, Wednesday, yeah, just like one hot encoded. That's problematic if there are many seasons. Now, what this gives you are these kind of abrupt changes, right? If you model, let's say, the day of months, you count here from 1 to 30, and then it goes back to 1, which is not great for some algorithms. So what people would then do is they would get these more continuous, like sine, cosine waves, and they're actually called Fourier terms. So yeah, so like you would often use Fourier terms as additional inputs for your method. Yeah. For deseasonalization, there are different methods like STL, MSTL, STR. Yeah, that deseasonalize, and then, well, as I say, we can deseasonalize the series and only feed the trend and remainder component into the algorithm. You can think about that as some form of boosting, where at first you use one model that models seasonality, and then the remainder you feed that into your machine learning model. It does put expert knowledge into the model, right? And I think the idea here is that if you do not have enough data to model seasonality, it can be a good idea. Well, if you don't have enough data to learn the seasonality from the data, it may be a good idea to actually do these decompositions beforehand, right? So what we've talked about before, this thing of, well, we have a monthly data set, 70 time series. We want our machine learning model to perform well. Yeah, you probably want to model the seasonality yourself and not leave it to the algorithm. Okay, yeah. Maybe let's skip about this one. Yeah, I think this is very important as well, the normalization, right? So because in some forecasting problems, the forecasts are within a pre-specified domain, right? Something like wind speed, wind power, maybe even electricity price. You know beforehand that all the values you will ever get are between, let's say, 0 and 25. So now normalization is very easy. You just divide by your maximum that you know you will never be over, and that's it, right? But in other time series, this is very tricky. So if you have things like share prices, web page hits, the price of Bitcoin, you know, businesses that just grow fast. I mean, one thing I often see is that a lot of research that we see is done in electricity, and in electricity we hardly have any trends, or they are very kind of small. And then you work in a company that is a startup company, everything grows a lot. So all the time series have these super strong trends. And then you need to use very different tools to model these time series. Yeah, so again, if the domain is limited, the scale has information. So if you are at 0, you know you cannot go further down. Then sometimes things happen like that. If the level is already high, trends tend to be less steep. You see, for a company that has currently 100 customers, it's obviously a lot easier to double their customer base. And for a company like Facebook that has 2 billion users, to double that is a lot more expensive, a lot more difficult. So steep trends will slow if your values go high. Yeah, so you can include information about the scale as an input. Error measures are often scale invariant. So I think the example I want to give here is this time series, right? So I've taken this air passenger series, I've made it artificially a bit even steeper. So, and now sometimes you see papers where people say, well, we do mean normalization because that's, you know, what you have to do. Now, if we look at this time series, in red, I've shown you the mean of this time series. So if we now divide this series by the mean, what we get is this series. So you see the values here, they are like to the power of 11. Here it's a value of 10. So we've brought it down to be values from 0 to 10, but the shape has not changed at all, right? So normalization here by just dividing by the mean has not helped at all. On the other hand, this what we've seen before, this per window normalization, that obviously works better. Okay, one quite important other point I want to make is this direct output versus iterative one step ahead. So these traditional methods, ETS, ARIMA, they all optimize for one step ahead accuracy. And now if you predict further out, let's say, you know, you have a daily forecast, you predict 1 to 24 points out, you feed back the forecast into the model. That can lead to error accumulation. And it's often better to predict all the horizons needed. And now methods like neural networks, they can have multiple outputs. They can have output windows with gradient boosted trees. What you can do is, well, they produce only one output at a time, but you can actually, you can iterate out. So you just feed back the forecast and iterate out the model. You can also build, well, obviously a direct model where you predict directly the horizon that you want, and then you can also do mixed forms of it. So I think that's something that is quite interesting. So let's say you need to predict 100 points out. You can build 10 models that all predict the next 10 days, and then you feed back these 10 points, and with that you get to the window that you need. So this is relevant if you want to go for really long horizons. So let's say you have a daily time series, you want to predict 400 days out, then you need to do things like that. Yeah, and also to mention the M5 winning method was actually an ensemble of direct and iterative models. Okay, just quickly checking the chat. Yeah, so gradient boosted trees, they were quite successful in many competitions, like GBM, the obvious choice. Cut boost performs ordered gradient boosting and is supposed to be especially suitable for time series. We've tried it, it works well, especially with its default parameters. Light GBM is still usually our go-to method. Yeah, seasonality and trend handling as discussed earlier, like Fourier terms, window-wise normalization. You build one model per horizon or for a subset of horizons, and then you roll that out if you need more. It works really well if you have many external variables, you do the feature engineering, and you can also use differences of the legs and the original legs, things like that. Yeah, then, well, holiday effects, obviously, monthly series, things like number of trading days in the months. You can put in promotions, out of stock events, weather, and so on. Yeah, and these methods, well, I mean, that was kind of the type of modeling that won the M5. I would still argue that even now, in many cases, you know, depending on your data set size and so on, that would still be like my go-to modeling method. And sampling works in forecasting just as well as in any other area of machine learning. It has been heavily used in Kaggle competitions, ensembles of gradient boosted trees, neural network, linear models like pool regression, even ensembles of local and global models. Yeah, and it's known under the term forecast combination and forecasting, and also there we know that it works. It's a long time. Okay, good. So I think, well, that finally gets us to, yeah, so this concludes like the part of how do you do kind of traditional forecasting. Obviously for the traditional, well, traditional forecast, I mean, forecasting with traditional machine learning methods, for that you obviously need to think a lot about feature engineering. We've talked about that. You need to think about how to deal with trend seasonality. Now we get to the deep learning. I mean, many of these deep learning models that we will look at, they actually internally also do things like Fourier terms. And many of them actually don't have any trend handling, and they are only tested on series that have hardly any trend, right? Like energy time series and so on. So keep that always in mind. Like with machine learning, the question is always, how do you deal with the non-stationarities? How do you deal with the trend? How do you deal with the seasonalities? And then some of these models would have that already built in, the seasonality handling at least, and then trends. It's a bit a neglected topic to a certain amount in the forecasting field because people often don't have trends in their series. So chances are that if you use a deep learning method on series with a lot of trends, that it's not going to work out of the box. Okay, with that, let's get into the deep learning, and I think I'll hand over to Abishek for that. If he's
Thanks,
here.
Christoph.
Yeah, okay.
Shall I share my screen or shall I use yours?
That's a very good question. What about I stop sharing?
Yeah.
Then you can share, because then I take a quick break and I'm right back.
Yeah. Okay. Okay, it's good. Okay, so let's look at some of the deep learning techniques for forecasting. So as we know, like deep learning is pretty popular methods to use today, and usually like the methods that people use for forecasting comes from NLP methods. So you look at people using RNNs, it's because we started using it because NLP space, it's very similar to time series where they have sequences, we have sequences. So it's very natural to adopt techniques from NLP into forecasting like LSTMs, attentions, and transformers, etc. Right? But there are also a lot of differences between NLP problems and forecasting problems. Because with NLP, don't really have this idea of the recent observations being more important than the others. But in forecasting space, that's a very common mentality, right? And then there is also long-term dependencies in NLPs. But for us, like long-term dependencies are usually very simple, and it's just seasonalities, which is very easy to predict usually. Well, there are a couple of good tutorials and materials on forecasting with deep learning methods, which we have listed here. If you're interested, you could check the references for them. And let's start with looking at the recurrent neural networks, right? Like, so recurrent neural network seems to be an obvious choice when it comes to deep learning because it works for sequence data in NLP, so it has to work here as well, right? And then the idea of that working is because of auto-regression, because it holds internal state memory where it remembers what happened in the past, right? There is a memory that holds there, and then so it's similar to how auto-regression works. But then in practice, we also include sliding window techniques like input and output windows, because that helps ease the process of auto-regression for neural networks. So you make the state less important, but focus more on the recent history by using those windows, right? And and then there are a couple of papers here we have listed, which talks about the best practices of using recurrent neural network for forecasting. And majority of them use majority of the recent papers use global model method for RNNs, but you can also model univariate series as a univariate model as well if you have enough length of the series. So if you have enough history, you could always go for that as well. And there are a couple of problems that RNNs face as well, right? So if you look at RNNs, we have the problem of vanishing gradient, which is a pretty common issue that people face when they train RNN models. But it's getting better. So if you use LSTM, it kind of mitigates the problem of vanishing gradients. But there is also it's still, the problem doesn't disappear; it still exists. So that's when like people started moving towards convolution neural networks, and convolution neural networks works a lot faster than RNNs as well, because you just have a 1D convolution and you act on the entire window. But the problem of convolution is that it doesn't have a state memory, which means that you should feed in entire seasonal window as your input windows, or like basically you need a long windows with dilations, since it doesn't see everything all at once. So there are a couple of other new techniques that are rising in CNNs as well, which are like temporal convolutions, dilations, and WaveNet uses causal convolutions. So there are other approaches that are slightly different from the traditional convolution approaches that are coming up, and it's being recorded and evidently proven that it's working better and a lot faster than RNNs as well. So if like you have a longer history of time series and you don't need smaller windows, the approach, CNN approach would be more preferable than RNNs. But for RNNs, especially with like time series with like short input windows or something, or like series with holes, or let's say irregular sizes or unequal sizes, lengths of series, RNNs would be a better preferred approach for deep learning methods. There are a couple of specialized architectures that have been published recently, which includes the DeepAR from Amazon, which uses a generative RNN model and does probabilistic forecasting. And then there is a deep state space model, which uses RNNs to parameterize the linear state space models. And then there is deep factors for forecasting, where they have they model two different patterns. One is the local probabilistic patterns, and then there is a global time series patterns, and they combine them together as to give a better. So the local predictions also understands what's happening in a global level of time series. And then there is NPEATS, which uses basis functions to decompose the series into seasonality and trend, and then they model the residual using a stacking architecture as well. So and NPEATS has really good evidence of working well because we have the M5 and M4 competitions where the winners have been using them.
Okay.
Can we get?
Yeah, let me talk about these, and then later you can. Well, let's see if we can go a bit quicker, and we still have time for the hierarchical stuff, and then you can talk about that. Let me share my screen again, maybe. Good. Yeah, you see that? Yes. Okay. Good. So talking about the transformers, yeah. So I mean, there are these early works of transformers for forecasting, like this temporal fusion transformer. The temporal fusion transformer, it addresses specifically common time series problems, like incorporating static and dynamic covariates, both past covariates and future covariates into the transformers. It helps you to obtain prediction intervals and so on. So I think, well, it's very good work in that sense. It's reported to work well in practice in many situations. So people are using it, right? It does work. Keep in mind, TFT was already in existence at the time of the M5, so I'm not sure why it was not used by any winning team. Maybe because the data was too intermittent. Yeah. Okay, and now since yeah, good question. Future covariate and past covariate. Yeah, true. I didn't explain that. So basically, a future covariate would be something that you already know is going to happen, something like a holiday, a promotion. So, for example, if you know, so we know 25th of December this year will be Christmas. So it's something about the future that we know. Whereas a past covariate would be something like, I know yesterday the price was this, and because of that, I feed that into my model to predict tomorrow's value. Yeah. So some covariates are known and others, yeah. Yeah, exactly. But so you need both. So the comment from the chat is you need both past and future holidays. Yes. But the way that you model it in your window, right? So in your input window, you put in only kind of you say, in this day, in the future, I know it's going to be a holiday, right? And sure, in your training set, you have known that from the past, so you modeled it accordingly. But conceptually, as the current input to your model, it's something that you know about the future. Yeah. Good. So yeah, now transformers. I mean, well, I've talked about it at the beginning. There are these foundational models, they are coming. So I'm by no means claiming transformers are not good for forecasting. But what I'm saying is that they are not the silver bullet, at least not right now, right? So sometimes they work, sometimes they don't. Let me tell you why I think that. So, I mean, since about 2019, there has been this myriad really of variants that people have come up with: informer, autoformer, ETS former, ROB former, FET former, and 10 others similar to these. I think, well, they all have their plausibilized ideas of why what they do makes sense and why it should work. So definitely. One thing that I find a bit strange is that they usually solve what they call long sequence time series forecasting, which to me seems a somewhat invented problem. Like, I don't know, or let's call it academic problem, right? So people solve this problem because the papers before them have solved that. But is that really a problem relevant in practice? I don't know. I mean, at least there are many other, it's only a small subset of what we would care about in forecasting. And now what many of these papers do is they evaluate on the same small amount of data sets. Yeah, as I said, that only represents a small subset of what you could encounter as forecasting problems. Strangely enough, they all use, or many of them use an exchange rate data set where they fail to benchmark against the naive forecast. And we actually have shown in a paper that many of them lose against naive. And even if they do win against naive, I mean, predicting an exchange rate 720 days into the future, which is basically 2 years into the future, you're predicting the exchange rate between, US dollar to euro. I mean, you tell that to a finance person and they're like, that doesn't make any sense. So be careful with this. Also, this exchange rate data set, it only has trading days in it. And then some people find like a seasonality of, cycle 7, cycle 30, things like that. And then I'm like, well, but your month is only 20 days long. So how can you find a monthly seasonality length 30? So there's another paper that kind of showed that many of them also lose against linear models, and that one really important thing is that most of the benchmarks they use in these original papers are one-step ahead methods that are then rolled out for hundreds of steps, whereas these informal models do direct modeling directly for like very large output windows. Yeah, and what this paper shows is that if you do the same thing with linear models, all directly trained, actually they are not as performant as they claim to be. Okay, so having said all of this as a cautionary tale, so I mean, I've seen here situations where, you spend 3 hours running on a very powerful GPU, you're training to get a result that is worse than naive. That's obviously a word of caution, but to be fair, I mean, people like Zalando, they have reported they use transformer architectures in production. They work well, but they obviously train on really large data sets. Like they have 350,000 daily series of product sales and so on. So if you have large amounts of data, transformers are probably a good method. If you have small amounts of data, you definitely want to benchmark against like the gradient boosted trees I've talked about before, and maybe even simpler methods, right? I mean, things like if you do electricity demand forecasting, a seasonal naive should be always your benchmark, and because it will be quite difficult to beat. Okay. And similarly, if you do like share price, exchange rate forecasting, naive forecast needs to be a benchmark. Okay, so now some resources, Gluon TS. It's a very nice library, Python library from Amazon that implements many of these deep learning architectures. Then our resource, forecastingdata.org, where we have a repository with many data sets. We have code and results where we run many of these methods, and where you will see that the results are quite mixed. Sometimes there are very small data sets on which transformer methods work well. And then there are relatively large data sets where other things work better. And now, of course, you could say, well, you didn't tune the hyperparameters properly, maybe, this and that. But the question is, if you use these methods in production yourself, then that's also a problem you will have, right? So like how to tune the parameters correctly and so on, I think that all goes into the mix. So in that sense, I think this is a quite realistic scenario where we run these methods, and maybe with very intricate understanding of how the methods work, maybe you could get better results, but I guess the same is true for every method. Okay, so let's have a look into multivariate forecasting. So we've heard before that it's not the same as global modeling because series can influence each other through cannibalization, substitution effects, and so on. I think it could be like the holy grail in retail demand forecasting. It's a quite difficult problem, active research area. Yeah, so the main problems, as I've said before, are like how to scale the methods to really thousands of time series, how to have products come and go, how to model changing relationships, and usually we have some sparseness constraints here. I mean, some methods I want to mention here is, well, a paper from 2016 about matrix factorization, then 2018 LSTNet. That's a quite famous paper where they do CNNs that feed into RNNs with skip connections. 2019, these are kind of the same people from 2016. Again, matrix factorization with some causal convolutions and attention. Then 2019, we have a paper from the Amazon team with Gaussian copulas. This method is actually implemented in GluonTS under a name called DeepVar. Then we have some graph neural networks. There's a paper Wu et al. 2020 where they kind of learn the graph from the data. Then Abishek, who has presented to you just now, has a quite nice paper from 2013 where we look at like how to initialize the adjacency matrix. Yeah, and I mean, this is still a quite active research area. We also have some work happening here, but very often these methods have kind of scaling issues. Yeah. Okay, forecast evaluation. That's a very important topic and one that I like to talk about way too much. So I thought maybe in this talk, let's keep it short. We've already had some, at least one question in the chat. So yeah, we'll have to skip this part today, but I think by now we have put together some quite nice resources. So I recently wrote a paper together with Hansika Hevamalage about forecast evaluation for data scientists, common pitfalls and best practices. So the question that we had in the chat about which error measure should you use. So in this paper, you know, we gathered all the error measures we could find in the literature. I think it's about 40 of them. And then we talk about when is an error measure good, when is it not good. The interesting thing is that there is no single error measure where you cannot think of a use case where it does, or a situation where it does something that you don't like. So yeah, it's surprisingly difficult which error measures to use. We have this paper covering it. I also wrote like a bit more an applied paper in the International Journal of Applied Forecasting about the same topic. I have a talk at ISF this year. You can check that out on my webpage. But apart from that, I think, yeah, we skip over this topic. And we get straight to the probabilistic forecasting. So yeah, I mean, that was also a question in the chat already, like how do you do, like, how do you get like a distribution, right? Because so far we've pretty much only talked about point forecasting, and many people would argue that a point forecasting in itself is not what you want. Like, you want a distribution, right? I agree with that to a certain amount. So yeah, so you have probabilistic forecasting, very mature research topic as well. These are all the topics, all the ways I've come across how you can do probabilistic forecasting. It's not an exhaustive list. I think there are others. But anyway, so what you can do is you can do analytical prediction intervals. You can do bootstrapping. You can use like a Bayesian model with MCMC sampling, for example. You can forecast the parameters of a distribution. You can do quanti-regression with pinball loss. You can do, and you can determine the uncertainty empirically through backtesting. That is also called conformal prediction. And you have another approach that is not as recent anymore, that is this level set approach, and another couple of approaches that I didn't put here. So let's start with the first one, the analytical prediction intervals. So this works well for some well-understood models. You would usually assume normally distributed errors. That's what ETS and ARIMA do, for example. And one problem that you have is that the intervals tend to be too narrow with that, right? So here I show you an example. The inner interval, that is, I think, 80% prediction interval, and the outer interval is 95% prediction interval. Yeah, the next thing you can do is simulation and bootstrapping. That's usually quite slow because you need to run the model many times. The intervals would be usually too narrow as well, because you consider normally, well, with like if you just rerun your neural network with different seeds on the same data, the intervals would be too small because they only consider the parameter uncertainty of the model, and they don't consider the data uncertainty and the modeling uncertainty. Yeah, you can bootstrap the residuals, or again, assume a distribution. Then you simulate forecasting paths by feeding back these bootstrap values. And well, if you want to know more about this, that's also in the FPP book. Yeah, MC sampling, that works well for certain models. We have a model called LGT, which is some like Bayesian exponential smoothing version that does that. It works quite well, but is slow. Now this determine uncertainty empirically through backtesting. Now that's an interesting one. So to me, I mean, my understanding is that this is really the same thing as conformal prediction, right? Conformal prediction obviously puts some theory behind it. It has been used by companies in practice for a long time. It leads to more realistic prediction intervals. You potentially need a lot of past data and rolling forecast, because so the idea is you have a validation set, and now you check kind of your method, how big do I need to make the intervals on this validation set for the intervals to have the right size. Yeah, it works well, but now you have this additional validation set. So the question is, well, how could we get rid of that? So you want to do some cross-validation or bootstrapping schemes as well. But this is a way that people nowadays use to just transform point forecasts to probabilistic forecasts. Yeah, forecasting the parameters of a distribution. So you could assume a normal distribution, and then you just forecast mu and sigma of this. That's actually what DeepAR does. DeepAR has a normal distribution and a negative binomial distribution. There's this NGBoost method, which is like a gradient boosted tree that does that. It was quite hyped in 2020 when it came out, but I've not seen it used a lot. I think it's quite slow, apparently. The drawback of this is you have to assume a certain distribution, which is good if you have a limited amount of data and knowledge of your distribution. But if you have a lot of data, maybe you want to just learn this distribution from the data. And this is kind of what you can do with quantile regression. So yeah, it's implemented, for example, in this Wen et al. 2017 paper. That's a quite nice kind of classic approach. You don't need to do any distribution assumption. It's fast to compute, easy to implement. The drawback is you only get certain quantiles. In practice, maybe just 5 or 7 quantiles are enough anyway, right? So do you just need a prediction interval, or do you need the full distribution? Yeah, with neural networks, you can even fit different quantiles at the same time. And you can interpolate between these quantiles to get a full distribution, which was done by this paper in 2019. Pinball loss function, I think I'm going to skip over this. Now the question is, how do you evaluate probabilistic forecasts? And I guess the message here is it doesn't get any easier than for the point forecast. So you can have this simple hit-miss rule, where you say, well, how many of my point, like if I have an 80% forecast interval, do really 80% of my actuals lie in that interval? The problem is you can come up with trivial solutions where you make the interval sometimes very small and sometimes very large. So you need to some other ways to evaluate as well. And then I think this one, I don't want to go too deep into it. So you have this mean scaled interval score that measures the size of the interval and then penalizes if you are lying outside of the interval by how much you lie outside of it. What is this? Okay, sorry. What happened? Okay, sorry, I somehow skipped to the wrong slide. Yeah, so MSIS. So then you have other measures like scaled pinball loss, weighted scaled pinball loss, CRPS, things like logarithmic score, energy score, variogram score. So yes, as I'm saying, I think my message here is just forecast evaluation is difficult with point forecasts, with probabilistic forecasts. It's also difficult, but there are obviously ways to do it. Okay, now we want to take the last 5 minutes maybe or so to go into some special forecasting problems. We actually, well, there are many of those, right? The ones I could think of are external variables, intermittent data, hierarchical forecasting, forecasting in retail, interpretability, causal inference. I have material for all of those, but I think we want to look, well, I wanted to look into intermittent data and hierarchical forecasting. I think we might, or well, maybe very briefly go into just this intermittent forecasting. So there's this classical method, Croston's method, where the idea is you have two series, one that omits all the zeros, and you only model the demand when it's non-zero, and the other one models the wait time between the events. And you can do exactly that. And then it uses simple exponential smoothing for both series. So now you can obviously do this, but with a way more sophisticated model than SES. That's what would be called like a zero inflated model, where you have one model that predicts the probability of zero and the second model that predicts the value under the assumption it's non-zero. You have some other, like you could use specialized loss functions. For example, the Light GBM has this Tweedy loss function implemented. And I think these are the two big approaches. And now which one works better? I guess it depends a bit on the amounts of zeros. Like if you have really like more than 90% zeros, I would probably try the zero inflated one. If you have fewer, then just try the specialized loss function. And with that, we get to the last topic, which is the hierarchical forecasting. And I think I'll hand back to Abishek for that. Yeah. So we have about 9 minutes left. So yeah, just go through that. And yeah, if
Thank
you
you.
have, yeah. And I try to answer some of your questions in the chat in the meantime. So if you have questions, just pop them in the chat. Yeah.
So let's go to hierarchical forecasting. So hierarchical forecasting is a very common problem you see in a lot of spaces where you have spatial data or different categories or different departments. And hierarchy is not just spatial. There is also temporal hierarchies as well, where you predict something at a weekly frequency, and then you want to sum them up to monthly frequency as well, right? So the problem with hierarchical forecasting is that they have to reconcile properly. So let's say that you're predicting sales at a particular store, and then if you aggregate them back to regional level, they have to be a perfect aggregate of it, right? So if you say, let's say I have 10 stores and each prediction is 10, and then I make another prediction for a region level and it doesn't match up, then it's probably not consistent enough, right? And there is a good overview by Rob Hangman, which we have cited here. So if you guys want to read more, you could look into that. So there are a couple of approaches to do this reconciliation to make sure that your lower level forecast or the upper level forecast are all consistent with each other. So the ways of doing that would be one way is a top-down approach where you predict the top level series and then disaggregate it to the bottom levels. So you build models only for the top level series and not for the bottom level. For the bottom levels, you just disaggregate them. And the question is, how do you disaggregate? One way of doing it would be using ratios from the past or train a model to disaggregate, but it's still challenging to do. And then there is bottom-up approach where you predict the bottom level series and then just aggregate them up by addition or something, right? But the problem is the bottom level series are usually intermittent or noisy. They don't have proper seasonalities or trends that you have in the bottom level. Imagine like retail scenarios, right? Like you have different products, and most products don't get sold at every particular store. So you have a lot of intermittent sales in individual store level, but when you aggregate them up, you get a better seasonality and trend at a national level or regional level. Then there is the middle out approach where you predict the middle level hierarchies, and then you disaggregate and aggregate them both to get the upper levels and the lower levels as well. Then there is the other approach, which is quite recent, the optimal reconciliation approach, right? So optimal reconciliation approach is where like you predict all the different levels and then reconcile them to make it fit perfectly or make it more consistent across all the levels. The way that you do that is by doing it in two steps. One step is your forecasting step, which forecast for all the level, all the series, and then the reconciliation step, where we use some kind of optimization to make sure the consistency is more forced upon it. So the way that you do that is least square optimization or min-t optimization. You could see the trace minimization paper from Vikramasumya. So those papers talk about how to do this. And then there is the other paper from Panagiotis. So this one talks about more about the probabilistic reconciliation, right? So when it comes to reconciliation, point reconciliation, okay, so you just have to make sure that it sums up to the higher levels. So it's pretty simple, pretty straightforward. But when it comes to probabilistic reconciliation, how do you say that it is, well, how do you make this reconciliation? So because you don't have a single point forecast, instead you have probability density. So how do you make sure that they are coherent across all the different quantiles, right? And then that's where this paper comes in, where they use the geometric view, where they consider each of these probabilistic forecast or the probabilistic density functions to integrate into one over all the different variables together. So which means that you don't just add up for each and every individual, but the formula is more like the marginal probabilistic density of the higher level should be the sum of all the individual variables of the probabilistic density functions of the lower levels. So in that way, you can model the probabilistic hierarchical forecasts. And some of the other works which involve machine learning techniques are being listed here, so you could look at those papers as well if you're interested. Then there are other new techniques that are coming up in the machine learning space. For example, the end-to-end coherent probabilistic forecast, where they do end-to-end training. So all the previous methods, you see two different steps. One is the forecast step, where you forecast for different levels or particular level, and then the reconciliation step, which aggregates or reconciles their forecasts, right? But then these approaches where they do an end-to-end optimization just focuses on one single optimizer that optimizes for both the forecasting and the reconciliation step, which is more efficient as well, but also since you optimize for a single objective, it's much more easier and much more better to use. But then the problem with these type of approaches is some of these approaches follow the regularization way of reconciliation, which means that these reconciliations cannot guarantee consistency, which means so it optimizes to be consistent, but in some scenarios, you won't have a consistent forecast where the bottom levels might not sum up to the top levels. And here are a couple of the repository where the end-to-end forecasting approach is existing. So you could look at the code there if you want to use them, and hand over to Christoph for the conclusion.
Ah, yeah. Okay. So we managed just in time. Wow, amazing.
Yeah.
Yeah. So, well, as conclusions, so, well, I think one thing we wanted to show you here is that forecasting as a field has come a long way. It's a great time to do forecasting as a machine learner or data scientist. Machine learning methods, they become more and more competitive, but still be aware of some of the common pitfalls for forecasting, such as evaluation, benchmarks, data leakage, and non-stationarity. Well, and actually so most of them, we actually haven't covered them too much today, right? So evaluation, benchmarks, that's all on this paper that I pointed to. We also talk about data leakage, non-stationarity. We talked a lot about that, like that you need to address that in certain ways. But yeah, with that, I think we conclude, and happy forecasting, everyone. Thank you so much. Good, I think that's it from us. We are on time. I mean, I personally could stay some more time and answer questions if you want, but obviously it has been 2 hours, so anybody who needs to leave, please feel free to do so, obviously. Thank you very much.
Thank you very much, Dr. Christoph and Abhishek. It was really interesting session. So let's give our audience another 5 more minutes to ask any question if they have. Would that be fine? I see one question on the chat.
Yeah, about the ensembling. Yeah, I think ensembling is always a good idea, right? So ensembling is as close to a free lunch as you can get, right? The only thing to be aware of with the ensembling is many methods already do make heavy use of ensembling internally. And the other thing is that ensembling works best if your methods are very different from each other, right? So ideally if you have like 2 completely separate teams that develop a totally separate solution to the problem, and then at the very end you ensemble these 2 together, that is what usually works best. Yeah, and also like the methods you ensemble together, they should be quite good already. So often if you just ensemble together one good solution and one that is a lot worse, that often also doesn't work. Yeah, exactly. So it was a quite quick going through everything. Yeah, I guess and well, obviously towards the end where we then really talked about, you know, the deep learning and the hierarchical stuff and so on, we only very briefly mentioned a couple of things. But yeah, I hope we gave you enough pointers for the literature. Okay, what's the recommended modeling approach in the context of retail forecasting? Ah, yeah, okay, true. Good find. I didn't talk about that. Yeah, so I think here it really depends, right? So the question is, how do you address forecasting in a retail context, for example, where there are lots of new products every year? I think it depends, right? So if you have no history, then you need to find similarity in some other ways, right? So if you say, I introduce this new product, what do I know about this product? I would have some meta information, and then it becomes more of a maybe a clustering problem where you say these new products are similar to these old ones. And in that way, you try to infer what could be their possible demand. That's when you have no history. Let's say you have 1 data point of history or 5 data points of history. So that's where maybe it could make sense to actually train a neural network, right? Because in a neural network, you can have a very short input window, maybe just 5 data points as an input window. You have the state that still models everything. So you don't need, like in a CNN, you need this large input window to cover all of your seasonality. So in that situation, often recurrent neural networks work well, because you have some series that have very, very long history and others that have just like a very few data points of history. But then apart from that, obviously global models are good because they would learn from the other series as well. So you don't have to predict with only 5 data points, for example. Yeah, and then that's it. I mean, some methods even claim that they can directly work with this out of the box, right? I mean, if you think of, let's say you use a gradient boosted tree. A gradient boosted tree can have missing values in your data. So, and let's say you have a lot of metadata that you put in as well, right? So you have an input window, but you also have a lot of other information about your products that you put in. And now maybe your whole input window is just NAs, but the method will hopefully still produce a reasonable forecast. Yeah, I think that's what I have to say about this question. Good.
Okay, it's been a very interesting session and very interesting few hours. Thank you very much, Dr. Christoph and Abhishek, for accepting our invitation and be our instructors for this session. We will share all the materials and the recordings soon, and really appreciate your session and your knowledge sharing with us. Thank you very much.
Thanks very much. It was good fun. Thanks. Bye-bye.
See ya.